Hello, and welcome back to another episode of Plastic Podcast, the show that tells the science and the story of our relationship with plastic. I am your host, Clark Marchese, and today we are serving plastic and chemical recycling. All right, before we jump into it, we always get started with the trivia question. And the question for today is, which of the following is the name of an active volcano on Antarctica? I'm asking you this in honor of Pine Forest Media's latest series, South Pole, all about the science of Antarctica, which can be found wherever you stream your podcasts. Your choices are A, Mount Terror. Yes, that is a real name of a mountain on Antarctica. B, Mount Erebus. C, Mount Everest, and D, Mount Murphy. Spotify listeners can answer directly on the episode page of the app, and everyone else can DM me on Instagram at Pine Forest Media for a chance to win a monthly prize. No cheating, and stick around to the end of the credits to hear the answer to last week's question and a lovely review from one of you. Okay, chemical recycling. That's what we're here for today. I got the chance to speak with Dr. Julia Vogel, a chemical engineer working with the Federal Environmental Agency of Germany, also known in German, forgive me in advance, as the Umweltbundesamt. We talked about what chemical recycling is, why we're doing it, and we also did an Are You Smarter Than a Fifth Grader style, breaking down 4 different types of chemical recycling and how they work, and whether or not chemical recycling has a role to play in the future of our plastic problems. Now, I've been very curious about this topic ever since I started looking into plastics. One thing to keep in mind, however, when you're listening to this, is that I was a lot smarter at the end than I was at the beginning. This is usually the case when you're talking to an expert, but when I went into this interview, I didn't know as much about chemical recycling as I do now. I approached the topics trying to compare chemical recycling and mechanical recycling, which is the kind that most of us will be familiar with. But in hindsight, I think that wasn't the best way to go about it because they're not meant to compete with each other. You'll learn as we go along that they have different intentions, different outcomes, and they're trying to solve different problems. And I know that there are places to critique both types of recycling, but if anything, chemical recycling could be used most effectively to supplement mechanical recycling rather than replace it. Okay, now we can go ahead and get started. All right, hello, Dr. Vogel. Welcome to the show. The first question I have is if you could just introduce yourself and tell us a bit about your research.
Yeah, sure. I'm Julia Vogel, and I will focus on work in the area of waste treatment. My main focus are thermal waste treatment processes, and lately a very big part of that is chemical recycling. We recently finished a big research project that was carried out by the RWTH Aachen and the University of Merseburg, and it has the title Assessment of the Potentials and Evaluation of the Techniques of Thermochemical Plastics Recycling. We always have very long titles, I'm sorry. And this research project focused on the evaluation of chemical recycling in terms of energy consumption and greenhouse gas production in comparison to mechanical recycling and energy recovery. And the final report will be published very soon.
Well, it sounds like there's a lot of stuff in there, so it makes sense that the title is very long. And I'm sure that we'll probably break down a lot of those words in there for listeners who might not have a science background. But that sounds like a very interesting project. When exactly is it going to be released?
Well, it's difficult to say, but I would say in like 2 or 3 months, it should be available on our website.
Okay, well, we will keep an eye on that. Before we get into it, though, I'm just curious. Chemical engineering, that's a choice. When did you decide you wanted to become a chemical engineer?
Well, already when I finished school, I thought about what to do, and I decided I wanted to do something in relation to the environment, as well, things like the accident in Chernobyl or the so-called forest dying in Germany made very big impressions when I was a kid. So I decided to study environmental engineering, and later I got a PhD in chemical engineering.
Wow, I can only imagine how much work that must have been. Okay, the topic at hand, chemical recycling of plastics. I had never heard of what this is before I started this podcast, so for anyone out there who was like I was 2 months ago, what is that?
Well, first, there is no official definition of chemical recycling, but it's widely agreed that it includes technologies like solvolysis, pyrolysis, liquefaction, and gasification. I think we'll go to these later in detail. So
we sure will.
In this research project that I mentioned, we worked on a definition that could be used as a legal definition as well. There, we referred to chemical recycling as a process in which the polymers from the plastic are completely or partially broken down into their components, and these then can be used for other processes in order to produce new polymers or other substances. However, fuel production from these processes is excluded from the term chemical recycling.
Okay, well, we're going to break down all of those words into their own polymers and monomers. Let's even start with those words, polymer and monomer. A polymer is a chain of molecules, and a monomer can be thought of as one link in that chain. So our DNA is a polymer, and the monomers of our DNA, if you can stretch your brain back to high school biology, you might remember the letters A, G, T, C, U, and those represent the different chemicals that make up our DNA. Plastic is also a polymer, at least the vast majority of them, and they're built up of a chain of many, many, many different kinds of chemicals. Also remembering there are many different kinds of plastics, and so the monomer chain will look different for each type. So not a lot of people have heard of chemical recycling. I'm wondering, when did we start using this process? How long has it been around?
Well, there is no such thing as a concrete discovery day for chemical recycling. The technologies that I mentioned before that are now used for chemical recycling have been known for centuries, but for other products like gasification or pyrolysis, for coal or biomass, and even for waste, we've tried that like for the last 20, 30, 40 years already. However, it hasn't been too successful, let's say it like this. There were successful projects like a gasification plant in Germany in the late 90s, early 2000s, but it wasn't successful due to the very high costs of the waste treatment that were applied there. And I think the term chemical recycling as such appeared sometime before 2020, maybe 2015, 2018, something like that. And then it replaced other names such as feedstock recycling or raw material recycling that were around for a much longer time.
Okay, so still relatively recent in the way that we're using it today. And also, it sounds like I might be hearing in there, if we were to compare chemical recycling and mechanical recycling based off of sheer amount, it seems like there's a lot less chemical recycling that happens. Is that correct?
Yes.
Maybe I'll also ask you quickly if we chemically recycle other things or just plastic.
No, we at least prefer if we would use the term chemical recycling only when we talk about plastics recycling.
Got it. Okay, so the plastic recycling that most people are familiar with is where you put your coffee cup into the properly colored bin, and if it's one of the lucky 9% of plastics out there, it gets taken somewhere and turned into another coffee cup or something else. Can you tell us how mechanical recycling and chemical recycling are different?
Yeah, well, mechanical recycling basically is you keep the material as it is. So the polymer, plastics are always polymers, or not always, but plastics are polymers, and those are not broken down. Their structure is kept intact, and the material can just be used as plastics again. So basically, the old plastic, to say it very simply, is molten, and you can form new plastic from it. Whereas chemical recycling really breaks down the polymers, makes it smaller into smaller bits and pieces, and those can be used for, in general, for any kind of new product if you put it in the chemical industry.
Okay, so with chemical recycling, you're after the chemicals inside of the plastic. That makes total sense, actually. Once you have these chemicals, it sounds like you can do whatever you might want with them. They could even be made back into other plastics, but you could also send them off to other industries or sectors that use these chemicals. Do you know what the majority of chemicals that are produced from chemical recycling are used for?
We have to differentiate between the different types of chemical recycling. So I'll start with solvolysis, and that produces the monomers basically from the polymers. So that can be repolymerized into new plastics. It's basically the building blocks of the plastic polymers that are produced in solvolysis. In pyrolysis or something similar, which is called liquefaction in an oil bath, they both produce an oil. as the main product. And this oil can be used as a substitute for fossil-based oils in the chemical industry. And gasification, as the name already suggests, produces a gas. And this gas also can be used as a raw material for basic chemicals productions.
Okay, and then I guess for the oil and gas that is produced, its applications could be so wide-ranging it's hard to know exactly what they might be used for.
Exactly. From those, you just use them as an input in the chemical industry where thousands of products are actually produced.
Let me ask another question too, because one of the problems we face with mechanical recycling is that not all plastics can be recycled. Can all types of plastics be chemically recycled?
No, they can't. First of all, it depends on the type of chemical recycling, because there are differences. Not every type of chemical recycling, like solvolysis or gasification, can be used for all plastics. And as in mechanical recycling, there are problems with very, let's say, dirty input, for example, or very mixed material, also depending on the type of chemical recycling again.
Got it. What about in terms of energy expenditure? Is one type more efficient than the other?
Well, chemical recycling is much more energy intensive than mechanical recycling. And therefore, also greenhouse gas emissions are higher for chemical recycling than for mechanical recycling, because it breaks the polymers down. So you start much earlier in the life cycle, basically, of plastics, and you have to go through more steps in order to produce a new plastic.
Okay, so more greenhouse gas emissions are generated in the process of chemical recycling, but maybe it's useful to look at the outcome. With chemical recycling, depending on the process, you're basically creating a fossil fuel substitute. So is chemical recycling more energy and greenhouse gas efficient than removing more fossil fuels from the ground?
Yes, always. Recycling is always more efficient. However, if you look at, for example, greenhouse gas emissions from those two processes, it gets a bit tricky because you have to look at the whole process, not just the chemical recycling process. And our research project showed that if you use pyrolysis oil instead of raw oil for new plastics, if you just look at the greenhouse gas emissions, they don't differ so much. But in terms of energy efficiency and all the other aspects, just substituting a material that you have to extract from nature is obviously, it's much more efficient.
How about cost? Is one more expensive than the other?
That's always very tricky to answer, but in general, I believe that chemical recycling is more expensive because of the type of plants that you need to build.
Okay, so let's dig into these different types of methods. We have solvolysis, liquefaction, pyrolysis, gasification. Listeners, don't worry too much. I'm going to be holding your hand through this, and Dr. Vogel is going to be holding mine. But maybe I'll first ask which of these is most commonly used.
At the moment, liquefaction and non-oil bath and pyrolysis are the ones that are, used the most or looked at the most. Solvolysis is very specialized for certain plastic types and is more on a laboratory scale at the moment.
I want to understand how each one works, so perhaps you can try and explain it to me as if I were a fifth grader, because I think that might be where I'll need to start. One by one, how about gasification?
Okay, you chose the most complicated one to start with. So,
Perfect.
Gasification uses very high temperatures, more than 1,000 degrees, in order to decompose the input material, in this case, plastic waste. And a gasification agent that is either oxygen or steam normally. And from that, a synthetic gas is produced. And this gas contains mainly hydrogen and carbon monoxide, but also methane, carbon dioxide, and nitrogen. And this can be used then for further processing and cleaning in order to substitute raw material.
Okay, gasification, you turn a plastic into a gas. This is going well so far. How about pyrolysis?
Okay, pyrolysis. I'll start with pyrolysis and liquefaction in an oil bath together because they are similar in terms of their main product. They both produce an oil, and which is like a hydrocarbon mixture. And this again has to be purified and then can be used as a raw material and input for the chemical industry. However, the technology itself is different. So a pyrolysis reactor is heated and the plastics are decomposed through heat only. There's no oxygen present in this reactor. So pyrolysis works at temperature around 400 to 550 degrees, and it normally results in a gas that contains smaller molecules or parts from the polymers that are broken down. So this gas then can be cooled down, and the gas condenses, and a liquid, the so-called oil, is then produced. Some parts of the gas remain and can be used for energy recovery for the process itself, and also some solid parts are present that need to be disposed of.
Okay, pyro, like fire, heat, into a liquid, oil, liquefaction, also into a liquid, oil. This is clearly not the first time you've had to explain this to someone like me. We've got one more, solvolysis.
Okay, solvolysis is basically the decomposition of the polymers into monomers by using a solvent. And that solvent is always specially tailored to the polymer. And here we look at different types of plastics like PET from bottles, or polyurethane that is, for example, used in mattresses and stuff like that.
So this is the one where the final product can be turned into other conventional plastics.
Exactly. You get the monomers or building blocks of the plastics, and then you can just polymerize them as you would do when you produce these types of plastics from virgin material.
So this next question I'm asking is because I read a paper of yours that was trying to get to the bottom of this very question, but are these chemical recycling plants that we have economically viable in current market conditions?
No, not really. The thing is, these types of not state-of-the-art technologies are always associated with a risk when you invest into them, because you don't just yet know how the market will be and all those kinds of things. So there's a risk, and obviously they have a very high investment cost as well.
Okay, so just to make sure I understand, or even to say it in different words, when we say it's not economically viable in current market situations, that means that it is still cheaper for companies to take raw materials from the earth than it is to fund these plants, perhaps because of the sheer cost, or also because the risk that investors do or do not want to take. Is that a good understanding?
Yes, I think that's perfectly right.
Okay. Then are we able to make a prediction as to whether or not these technologies will be able to obtain the necessary funding and investment to make them viable?
Well, the question is maybe also, do we as a society really want that? And for example, if we have legislations that force producers to use recycling material, then we will also enforce any kind of recycling, really, because then it's not a matter of cost, but the companies have to invest. So they only would have to think about which technology they choose. And if mechanical recycling is not able to actually reach what we ask as a goal, then they will have to invest into chemical recycling. So at the moment, it's difficult to say what will happen, because there are also other options where we could go, but a lot of companies are planning to invest into chemical recycling.
So we mentioned that it is more ecologically costly to take raw fossil fuels from the ground than it is to chemically recycle, but there is a considerable amount of emissions associated with running these plants. I'm wondering if there are any other ecological drawbacks than the greenhouse gas emissions we mentioned?
Not really. I think it's safe to say that, let's say, under sound environmental management in countries that have a sound system in place, it's very unlikely that it causes any environmental harm. Yeah, as I said, it's more problematic in terms of CO2 emissions or energy in general than mechanical recycling, but obviously it produces less CO2 than incineration of plastic waste.
Another thing that the article you've written states is that there's still a need for future research to make final conclusions about the role of chemical recycling in the future. I'm wondering, what knowledge gaps do we still have? What research questions do you think still need to be addressed?
That's a bit tricky, that question. Well, in general, I think we got a bit further with like finishing our research project now that I mentioned before. because it shows that chemical recycling really can have a part in a circular economy and could have some positive impact as well, even if we still prefer mechanical recycling wherever possible. I think the questions that are still open are which waste streams are really suitable for chemical recycling, and with which technology is it best to treat those waste streams. So on the one hand, there are academic questions that can be a part of a research, but also these questions are probably decided by a market situation or the political framework in the future.
Based off of the waste streams that you just mentioned, maybe I should have asked this earlier, but just to clarify, is the waste stream currently different from mechanical recycling, or can you use the same well-sorted, proper plastic type as you would for mechanical recycling as you would for chemical recycling?
Well, you could use it, but you shouldn't. So
Okay.
it should be a stepwise process, basically. First, all the kinds of plastics that could be recycled mechanically should be recycled there because it's more efficient in all terms, cost, energy, and emission-wise. And all that is not mechanical recyclable could or should then go into chemical recycling. But even there, not everything will be recyclable.
So this next question, I think based off of the discussion we had, the answer might be obvious, but I'm going to ask it anyway because I think it's important to mention. And it gets to what a lot of plastic researchers are telling me when I speak to them, is that we will not recycle our way out of this problem. And they're referring to mechanical recycling. But for someone who's never heard of chemical recycling, we might think, oh, there's this new state-of-the-art technology. Maybe that's the answer to all of our problems. Is that the case? Is chemical recycling our answer to the global problem of plastic?
Unfortunately not. Yeah. The problem is it can be a part of a solution, but it's in general very problematic to expect that the waste industry at the very end of a life cycle of a plastic product deals with all the problems that have been created before. So we have to start much earlier in this, like, let's say, life cycle of a plastic product. And we should really get the producers to take their responsibility in order, for example, to make products that are recyclable, or to make producers responsible for the recycling of their products themselves. So there are many options to improve the circularity of products. Yeah, in order to solve our plastic waste problem, we really have to start much earlier, and we have to include many more stakeholders than just the waste industry.
Yeah, I mean, that tracks with what every other scientist is telling me. So thank you for reinforcing that. As we start to round out this conversation, maybe I'll ask if there's a piece of good news that you can share in your field, or something positive to end on.
I think I can say, and I think that is very positive, that a lot is happening in the waste industry at the moment. And in general, a lot of new things are coming up there. So I think this is good news.
Okay. Then the final question is there anything we missed? What else do we need to mention when it comes to chemical recycling of plastics?
I don't think we really missed anything. It's just, I want to stress that it's much more complicated than introducing some new technologies that will fix everything. You always have to look at the big picture.
Okay, I think that's a perfect note to end on. And the final question is, where can people find you and follow your work and access this report when it comes out?
The German Federal Environment Agency has a webpage where you can find all our topics. It's very informative, and also all our reports are published there and can be downloaded for free. And this is also where our most recent report will be published on chemical recycling. And also that you can have a newsletter or follow us on social media so that you're always on top of what we're doing.
Okay. Well, this is the part where I say thank you so much for taking the time to speak with me today. Thank you for teaching me about chemical recycling, and thank you for your really important work in this space.
Thank you for having me.
Okay, a major thank you to Dr. Julia Vogel. I hope you feel like you learned as much listening to her as I did speaking with her. It seems like the future of chemical recycling is unclear for the moment. Of course, we know that recycling, mechanical or chemical, isn't going to be the end-all solution to the plastic problem, but there could be other problems. Fossil fuels are finite, And of course, the fact that they will run out is not the only reason we need to be moving away from them. But it seems like this is a very moving space, so I'll be curious to see if chemical recycling is the direction we decide to move in or not. And I think our brains did enough work for today, so I think I will leave it there. You've been listening to Plastic Podcast. You can find more information about this week's guest and links to their work in the episode description. Cover art for the show was done by Laurel Wong, and the music you're listening to was done by Tadeo Gabejos. I am your host, Clark Marchese, and this episode was produced, written, and engineered by me. So if you found it interesting, send it to someone you know. Plastic Podcast is part of a larger network of sciencey podcasts called Pine Forest Media. You can find more information about us in the episode description, or on our website at pineforestpods.com, or on Instagram and TikTok at Pine Forest Media. We've got some exciting sciencey podcasts coming out this year, and a 5-star rating across platforms and a review on Apple Podcasts is one of the best things you can do to help the entire network to grow. Thank you to all of you who have made it this far, and today's review comes from Kieran from South Africa, who says, "Part of what's so nice about the way you structured it is that it makes me feel really smart, in the sense that you've explained it in a way that doesn't make me feel stupid, but it's just the right pitch of making me understand it without babying me. Anyways, it's an enjoyable experience." If you would like your review to be featured on the show, all you've got to do is leave one on Apple Podcasts and you will probably get picked. Now for the answer to last week's trivia question. The answer was Paris, France. Paris was the place where countries from around the world met and agreed to work together to keep emissions from raising global temperatures above 1.5 degrees Celsius, and this agreement is thusly named the Paris Agreement. All right, that's all I have for today, and we'll talk soon.